So for this video, we'll be looking at problem 3.20 in the fundamentals of heat and mass transfer. To start out, we'll just look at the problem statement, and I'll highlight some of the important things that we have written out in the given here. So a composite wall separates combustion gases at 2,400 degrees Celsius. So we have Tg from a liquid coolant at 100 degrees Celsius. We have TLC with a gas and liquid side convection coefficients of 25 and 1,000 watts per meter squared Kelvin. The wall is composed of a 12 millimeter thick layer of beryllium oxide. So we have the thickness on the gas side, and then 24 millimeter thick slab of stainless steel. So we have that thickness too on the liquid side. A schematic for this is shown below, but the contact resistance between the oxide and the steel is 0.05 meters squared Kelvin per watt. And in this problem, we're looking for the rate of heat loss per unit surface area of the composite. So that's highlighted here in the find. And also at the end, we're going to look at the temperature distribution from the gas side on this side to the liquid side on the right. So we looked at the givens a little bit, and they're written out here. Next, while we think about this problem, we're going to be using thermal resistances and thermal circuits to solve this. And we're also going to be considering the contact resistance between these two pieces of the composite wall. So the equations are shown in the middle of the screen right here. And these are the main equations that we'll be using for this problem. As you can see, the resistance for conduction is the length over the thermal conductivity times the area. But because we're looking for the heat loss per unit surface area, we're going to be using R double prime instead of R. So it'll just be the length over the thermal conductivity. And then for convection, it's the same thing. We're using R double prime instead of R. So we'll be using 1 over H to find the resistance from convection in both the gas and the liquid. And what we're looking for is Q double prime. So to find this, the equation for that is the change in temperature, which is known because we have T infinity on the gas side and T infinity on the liquid coolant side. So it's the change in temperature over the resistance. And that's the total resistance between the two temperatures. And we'll also be using the other two equations a little bit later on. But we're able to do this because of some of the assumptions that we're making. So some of the bigger ones, we're neglecting radiation. So we don't have to worry about that at all in this problem. This is steady state and 1D conduction. So we're able to use thermal circuits to solve this problem. And then also we'll be assuming constant properties. And to be able to actually solve the problem, we need to assume different temperatures for the beryllium oxide and the stainless steel in the composite wall. So here are some assumptions that I made for that. I said the beryllium oxide is 1,500 degrees Kelvin, and the stainless steel is around 600 degrees Kelvin. And then using certain tables in the book, table A1 and table A2, we were able to find the thermal conductivity for both the stainless steel and the beryllium oxide. And those are pointed out here. So now that we have the problem all set up, we're actually going to go through the analysis. I actually have thermal circuit already set up here, but I'll talk through it quick. So all of these are in series. We don't have anything running in parallel, but to zoom in, we have the temperature of the gas, T infinity G. That's separated from temperature T1, shown up here, by the R convection in the gas. And then separating T1 and T2, we have the conductive resistance of the beryllium oxide. And then between T2 and T3, we have the contact resistance between the beryllium oxide and the stainless steel. For T3 and T4, we have the conductive resistance of the stainless steel. And then between T4 and then T infinity of the liquid coolant, we have the conductive resistance, or the convective resistance, sorry, of the coolant. So with this, we'll now be able to set up our equations for finding the rate of heat loss and then also all of the different resistances we'll be looking for. So I actually have a more in detail picture here. It's the same picture as above, but it also gives the different conductive and convective coefficients and also the different thicknesses we'll need to solve these equations. So now we have the equation for Q double prime, or the heat loss per unit area, which is delta T over R double prime total. And that equation is shown right here. But to find R double prime total, you're adding the convective, the conductive, the contact, the conductive, and the convective resistances all the way from T infinity on the gas side to T infinity on the liquid coolant side. So to solve for the first one, for number one, we have R double prime of the convection on the gas side. And from the equations that we saw before, that just equals 1 over Hg, which is the convection coefficient for this gas. And that's equal to 1 over 25 watts per meter squared Kelvin. So then we know that R double prime convection is 0.04 meters squared Kelvin per watt. And we'll also go through number 2 for conduction. So we have R double prime conduction. And this is in the beryllium oxide. And we know that this equation is L over K, and that's equal to T thickness of the beryllium oxide, which I have highlighted up here, over the conduction coefficient of the beryllium oxide. So for that, we have 0.12, 0.012 meters over, we found the thermal conductivity to be 20 watts per meter squared. Yeah, 20 watts per meter Kelvin. And this gives us a thermal conductivity of 5.588 times 10 to the 4 meters squared Kelvin per watt. And I actually, just to save some time, I have the rest written out here. It'll be the same. So we already solved for 1 and 2. The third resistance is just the contact resistance, and that was given to us. The fourth resistance is actually the same system as the second because it's conduction. So that's shown here, the length over the thermal conductivity. So we have the thickness of the stainless steel over the thermal conductivity to give us that resistive coefficient. And then the last one is conduction, which is number 5, which is just, or convection, sorry, which is just like number 1 for the convection on the gas side. We have the convection on the liquid side now. And then if you sum all of these together, you get the total resistance. So once you have your R total, or your R double prime total, you're able to find Q double prime, which is the first thing that we were looking for, which is the delta T over R double prime total. And that's equal to 2400 degrees Celsius minus 100 degrees Celsius all over 0.09276 meters squared Kelvin per watt. So with this, we found Q double prime is equal to 24,795.5 watts per meter squared. So now that we have Q double prime, we want to find the temperature profile, which is the second thing we were looking for in this problem. So for the temperature distribution, I actually have it written out here already. As we saw above, Q double prime equals delta T over R. So we can solve for 2 different equations for convection and conduction that we'll be using to find the temperatures for T1, T2, T3, and T4. As you can see, it's just T1 equals T2 minus Q double prime over H for convection, and then T1 equals T2 minus Q double prime times L over K for conduction. So to find T1, we're going between T1 and T infinity on the gas side. So we have T1 equals T infinity on the gas side minus the Q double prime that we just found in our last step over the the convection coefficient for the gas. And if you plug the numbers in, you'll get 1,408 degrees, 8.2 degrees Celsius. So then for T2, we'll be using the conduction equation, and that's between T1 and T2, and the conduction is through the beryllium oxide. So to find T2, we have T2 equals T1 minus Q double prime, and then multiply that by the thickness of the beryllium oxide, and divide that by the thermal conductivity of the beryllium oxide. And when you plug those numbers in, you get 1,393.3 degrees Celsius. Then to find T3, it's actually just the thermal, the contact resistance between the two materials. So that's right here. So for this, it's actually T3 equals T2 minus Q double prime times the contact resistance that we were given. When you plug these numbers in, you get 153.3 degrees Celsius for T3. And then for T4, it's another conduction example. So we have T4 equals T3 minus Q double prime times the thickness of the stainless steel over the thermal conductivity of the stainless steel. And plugging those numbers in, you get 123.78 degrees Celsius for your final answer for T4. So with these numbers, we're able to update our original schematic. So we have T infinity of the gas is equal to 2,400 degrees Celsius. T1 was equal to 1,408.2 degrees Celsius. T2 was equal to 1,393.3 degrees C. T3 was equal to 153.53 degrees C. And then T4 is equal to 123.78 degrees Celsius. I believe T infinity of the liquid was equal to 100 degrees C. As you can see, if we didn't consider the contact resistance between the beryllium oxide and the stainless steel, there would be a major difference in the temperature distribution here. The temperature distribution between T2 and T3 had the biggest jump, and I think that's super important to point out. Also, something else to consider that is important to note. Starting the problem, we had to assume temperatures for the beryllium oxide and the stainless steel. And we assumed 1,500 Kelvin and 600 Kelvin. Now that we went through this process once, if we want a more accurate answer, we would be able to iterate and go through the process again, and then look up the thermal conductivities for a beryllium oxide closer to around 1,400 degrees C. And for the stainless steel, the thermal conductivity, we would want to look up closer to around probably 140 degrees Celsius. So with that, we were able to find the Q double prime using the delta T over the total resistance equation. And we were also able to find the temperature distribution after we found the heat loss per unit surface area of the composite.